Okay, so we can go ahead and get started. So it's my pleasure to introduce our Colloquium speaker today, Professor Markus Raschke from the University of Colorado in Boulder. He's with the Department of Physics and Chemistry, as well as JILA, the Joint Institute there with the National Institute of Standards and Technology. He received his PhD in 2000 from the Max Planck Institute of Quantum Optics and the Technical University of Munich in Germany, and in 2006 moved on to the University of Washington before joining JILA in 2010, I believe. He's a fellow of the OSA and the APS and the American Association of the Advancement of Science, and he's going to tell us a little bit about his group's workings with accessing structure, coupling, and dynamics of matter on its natural length and timescales. So, Markus, thanks.
All right. Yeah, thanks a lot, Jason, and thanks a lot for the invitation. And a lot of familiar faces I met today. It was a really fantastic opportunity, really, to actually connect to people working in very related areas, in particular in imaging science, which is the primary focus of our work. And one of the is the microphone actually working, sort of? Do you hear me okay? Yeah, okay. So the primary focus of the work is to push optical resolution in spatial resolution in imaging to the nanoscale, and in a very generalized form, in any form of optical light-matter interaction, particularly in dense matter. And this is a key factor where we are learning now increasingly in material science that a lot of functional materials are heterogeneous on the atomic to mesoscale, and this is actually often what defines the functional properties of the material. This is true in intrinsically heterogeneous material systems like soft matter, where you have often multi-component molecular matter interacting. We are a living example of that. But it's also the case in many quantum materials, and I show you some example, whether it's in 2D materials or in correlated electron materials, which are nominally homogeneous. But in particular in correlated systems, as they undergo quantum phase transitions, you actually often see competing phases which form complex nanoscale textures. And so the goal is really that we can push optical imaging into this regime of down really to atomic scale, including access then not only to the structural problems but also to coupling between either quantum phases or between heterogeneous molecular phases. Then associated with it, of course, the ultrafast dynamics, which goes along with the electron or lattice interactions. And that's why I define it really that we are trying to aim to really probe matter on the natural length scale given by the electron and nuclear motion and the associated typically femtosecond to picosecond timescales. And in short, the tool of the trade here is actually that we try to do this through taking advantage of the light-matter interaction in the near field, which has actually many features beyond the simple access to very high spatial resolution, but also really increasing the light-matter interaction and actually providing new momentum states of light, which increases then the range of selection rules you can do in optical imaging. So this is certainly an effort in the group over now about a decade, and really due to a lot of dedicated efforts of current and past grad students and postdocs, and I'll sort of give a cross-section here of the work of several senior grad students and postdocs, notably of Eric Miller, who's a chemical physics postdoc, who is actually looking for a faculty position right now, and I can only envy the department who will have a chance to actually hire him. More junior, Omar and Tao, who recently joined the group, working in particular in the quantum material side of things, and in combination with a number of students. And I'll also emphasize work from a former grad student and postdoc, Sam Berwiger. Joanna Atkin did some of the work, which I'll talk about in the molecular systems, also who is now faculty at the University of North Carolina, and a number of other people. A lot of the work is collaborative. We develop more from the optical imaging side the method, and we work typically with a range of collaborators on the material side. If there is anything in particular you like about the technique, we actually reached out to develop national user facilities for nanoscale imaging, either laser-based. This is at Pacific Northwest National Labs, so most of the work is with DOE National Labs, or using synchrotron, broadband infrared radiation. We have a facility which we accept user proposals at the Advanced Light Source in Berkeley, and if you want to go to the southern hemisphere to escape maybe the hot Tucson summer, I'll recommend that you join us in Brazil at the synchrotrons that was there. And then there is a number of industry collaboration which goes along with this. So maybe sort of a little bit for the pedagogical perspective, and maybe for students new to imaging science, I'll give a little historic perspective how we sort of got into this field. And, you know, Gary Larson cartoon is sort of hard to explain. Either the whole audience loves or nobody loves. But there is actually one interesting aspect, actually, about this image. And this is, it was actually in biological matter, where microscopy really took the foothold, recognizing that it is actually, in particular in biology, the interaction of in the concerted motion of different molecules in these heterogeneous phases, as you wish, which is responsible for the function. And this was actually what triggered a lot of the development, which in some interesting way, and I had interesting conversations this morning about this, also from a philosophical perspective, that the development of microscopy, of looking at smaller scales, was actually at the same time people started to look at larger scales. And this is because when you take the Galilean telescope and you invert you look through the eyepiece, you get a magnified image of the object. But really what the idea was born that this could be potentially useful was that one of the discoveries in early days astronomy was, of course, that there is structure of the universe inaccessible to the unaided eye. And the same idea was then, when you look the inverse through then the Galilean telescope in the performance of a microscope, that you may actually see structure which is relevant for the function which is not accessible to the unaided eye. And this really then led to, in fact, this very famous first image, actually, of a cell structure, then in this case, then moved from Italy to Netherlands, which were very advanced in lens making, and there were a lot of tricks, and I can talk a whole hour about the history of microscopy. But where it was really recognized, the cellular structure as the first level in the hierarchy of biological materials relevant for what the plant actually does. Now, the evolution of optical microscopy then took many routes, increasing in terms of spectral content, sensitivity, and so forth. And then most recently, as many of you know, reached then, even in far field, past the notion of diffraction limit, even though this is debatable nomenclature, where you actually reconstruct the point spread function center of gravity by taking advantage of fluorescent labels, which you can trigger to emit in stochastic fashion, and then you can reconstruct an image also way below the diffraction limit. Now, one problem, of course, with this technique, it's not readily generalizable. It's hard to use for dense matter in particular, where you cannot simply label it and you would actually lose the function, which is the case in a lot of quantum materials and a lot of soft matter systems. And it's largely limited to fluorescence imaging, where it's extremely powerful if you have sparse emitter and can label a system like in biological materials in a liquid environment. So really the more general picture of what you would actually really like to access is on the fundamental level, the interaction of the electrons and the lattice in molecular and hard matter, where you really want to push into the few nanometer scale, looking at as short as the processes which govern electron-electron interaction, or then at longer dimension electron-lattice interaction, or then the associated time scales, which are very fast because of the high electron velocity near the Fermi level, and then somewhat slower motion due to the lattice because of the finite mass. So to sort of illustrate this is a good example to look at what is actually responsible for the reflectivity of a metal surface, and what is sort of the microscopic elementary process responsible for this, to tell you how actually length and time scale are really correlated. If you actually take the Drude-Sommerfeld model for the conductivity of a metal, then from the electron density, you can then get an estimate of the scattering time, which is responsible for the finite resistivity of the metal. And then you actually find that you typically have electron-electron interactions, or electron lattice scattering, or defects or phonons on the order of 30 femtoseconds. And then if you know what the Fermi velocity is, equivalent to about 10,000 Kelvin of the electron temperature, then you can see that these interactions occur every 40 nanometers on statistical average. And so it's really this elementary time and length scale which really defines the entire electronic and optical response of the metal, and this tells you that this is actually what we like to probe in a generalized fashion. Now, there has been a lot of developments actually associated with the advance in optical imaging to higher and higher spatial resolution and spectral content sensitivity with other probes, in particular electron and X-ray based imaging, where in both modalities we are now able to generate extremely short X-ray pulses, which allow you then also for time-resolved X-ray diffraction and imaging, and the same also for electron interaction as a probe for getting imaging contrast, whether it's actually in scanning tunneling microscopy or actually in free space electron interaction. The features of these methods, of course, rely either on the finite mass of the electrons, providing you then with the short de Broglie wavelengths, or then the short electron X-ray wavelengths associated with a high photon energy. But to really probe then, say, these electron lattice interactions, these are occurring at the milli-electron volt to electron level. And this corresponds then to light at optical frequencies out into the infrared, the mid-infrared. And so it would be desirable to really have the spatial resolution which these techniques provide, yet at lower photon energies. And so a way to think about this is actually then not too much to think about the wavelengths of the light in the sense of what the diffraction limit is, but really more in the sense of the momentum of the light, because this is sort of a more easier way to think about what actually the optical near field provides, because it's not just that we are sort of getting this deep sub-wavelengths resolution in near field imaging through sort of a virtual confinement of the wavelengths, but actually through an increase in this momentum state of this photon field. And so if you actually solve the wave equation then in the non-propagating form, which gives you the evanescent modes, and I'm sure many of you have done this in your classes in optics and electrodynamics, then you actually see that these momentum states of this near field is actually much larger than the far field momentum states. And this is actually what's responsible, in fact, that we are now getting confinement to sub-diffraction or deep sub-wavelengths dimensions of this evanescent field, and therefore we can do optical near-field imaging based on this field confinement, which really gives you then the super-resolution imaging, in fact, with all optical modalities, because this process is generalizable. And the simplest way of doing this is actually if you have any form of a nano-probe object, we use a scanning probe tip in the scanning probe modality. You can, in fact, look at many other also termed super-resolution far-field methods where you look at molecular emitter as a probe. So in many of these in these interactions, whether you look at the fluorescent energy transfer process, which are also a near-field interaction. So when you basically have this nanoprobe, it is this spatially confined and momentum space increased confined field which is responsible for the high spatial resolution, which of course then requires that you scan this tip in very close proximity to the sample on the order of then the dimension of this radius. And it is then this radius also which provides a metric for this momentum, because then it's the inverse of this tip radius which gives then the corresponding increase into this regime of these high momentum states. And when you think about this is a few nanometer apex radius which you can make with metallic tips which actually perform here as an optical antenna, then you actually see that you actually get X-ray momenta at optical frequencies. And if you do that, that also means that when you normally plot optical transitions vertically in momentum space in a dispersion diagram, then now we actually can also access new optical selection rules, because we are no longer confined to sort of these vertical transitions in these momentum diagrams. So these are sort of the key features again. So we have deep sub-wavelength spatial resolution to a few nanometers with new optical selection rules. And this is essentially what the talk is about. And I'll show you basically a number of examples and directions we are pushing this technique, and where I invite everybody to be interested, hopefully, in joining these directions. It's really an emergent field. Maybe a few more words on actually the history of it. the early idea of being able to actually confine light to really sub-diffraction dimension was actually the Irish, actually self-educated scientist who actually proposed this in a letter to Einstein to say, well, what if I actually take, in fact, a small aperture, I put it in my diffraction-limited focus, and then I'll sort of capture the light, which will then emerge out of this aperture, and then I can move this aperture around. He recognized correctly that you have to put this aperture close to the sample by a dimension sort of to first order given by this aperture diameter. In some way, this was an ingenious idea, especially at a time where people couldn't imagine actually how are you making apertures that small before you had e-beam lithography and other techniques. So it was actually ironic that Einstein actually commented this and actually criticized the idea for being practically impossible. But he recognized the ingenuity of it and said, well, you should publish it anyway. So this is actually how this work got into the literature. Now, in some way, when scanning probe microscopy was developed in the 80s, which then really allowed this capacity to have the ability to have sub-wavelength apertures in the form of tapered fibers with a metal coating, which was then the technique called near-field scanning optical microscopy, that sort of led to the practical implementation of this method. But there are a number of disadvantages running this with an optical fiber. It is actually that the transmission through a sub-wavelength aperture scales extremely unfavorable to force order in this radius. The longer the wavelengths, then you have a lambda to the fourth dependence in this transmission. And so this is why this technique was largely limited actually to fluorescence spectroscopy. In some way, was following this original idea, yet had extreme practical limitations, which led to that it's only used in some niche application currently. The idea actually of the inverse picture, according to, you can think of this as Babinet's principle, where you're confining sort of in a waveguide a propagating electromagnetic mode, which would correspond actually to sort of a magnetic mode around a freestanding wire, which then actually turns this concept where you then say we don't confine the light inside, but we externally illuminate a metal wire into an antenna problem, where we now drive an optical frequency and electric current, which actually increases the capture cross-section of the system, yet leads to this localized confinement of the field. And then you would look at the scattered emission from this near-field light-matter interaction. And this is why this technique was then coined depending on sort of what people initially thought is the relevant parameters, whether it's a scattering effect out of this, where this evanescent near-field interaction leads to scattering of the emission, or whether it's actually then this local field enhancement as a result of then when you do the boundary conditions of this confined object, right, then you get a locally enhanced field, and they thought then it's this tip enhancement which is relevant. I'll show you actually later that it's in some way you can look at it that both effects are equally relevant, or actually none of them is actually relevant, as I'll show you in a moment, because this is what we then discovered, that it's really more the optical antenna effect, which leads to this transduction of this incident field and an enhancement of the density of states responsible for the contrast we see, where these are sort of peripheral feature more interesting in the discussion of actually how we are detecting the signal and how we are then doing spectroscopy on it. So this idea of scanning near-field microscopy, though, then combines two key attributes. For one, as a scanning probe technique with very high spatial resolution, it gives access to the structure of matter. Being able to do this for any optical frequency, essentially all the way from the visible or UV out in the terahertz, gives you the spectroscopic capability, then with very high time resolution, so we get dynamic access. And if we actually now interact the tip with the sample, say through atomic force interaction as a manipulating tool to control this distance, then we actually retain all degrees of freedom which are non-interacting with the optical frequencies to still control sample properties. Whether it is actually a change in temperature, we can apply strain, and unlike in STM, we can actually apply magnetic fields or electric fields and driving a system through quantum phases. And so essentially what you measure is you're driving this interaction here with an incident laser field as an optical transient in some form, and then what the near-field interaction gives rise to is then a response function which will detect as a radiated emission. And this radiation is actually mediated through the tip. And so if you want to write an accordingly an appropriate equation, you can resort essentially to the conventional form of how you express an optical polarization driven in linear order by this electric field, or then through a combination of electric fields transients in nonlinear fashion. Then you are able to have ability to reconstruct what is the optical susceptibility of the material in first or second or higher order, which is a result then of this field confinement and the interaction localized with your with the system you want to probe. Of course, it is the antenna property and its response with respect to the driving field, with respect to the detected field, and with respect to the polarization characteristics. But all of these we can lump into Fresnel factor analogs, which describe essentially the antenna response itself. And so if you actually change the distance between the tip and the sample, you can extract all these extrinsic terms which describe sort of the system response without the sample. And then when you look at the response of the coupled tip sample system, and then you can reconstruct essentially the local material response, whether it's in linear or nonlinear order. Here's again sort of a summary of the parameter space we can access. We can get about 10 nanometer spatial resolution, in good cases down to maybe 5 or even 3 nanometer. We have the full wavelength range covered over all relevant milli-eV to electron volt interactions, and then we can do this with extremely fast time resolution. I'll show you an example in the end. The tip is, of course, the tool, and I mentioned already that the optical antenna properties matter. So we can engineer structures where we either have resonant interaction of the driving field with sort of then finite length metal wire. We can transduce the excitation into this apex localized field through combination with photonic crystal structures. One primary tool I'll show you in the end, because this allowed us, in fact, to do very high contrast nonlinear ultrafast imaging, where we couple the light actually by not directly illuminating the apex, but having a coupling structure distant from the apex, where we launch a propagating surface wave which adiabatically compresses into the apex, so we can really generate a few femtosecond pulse in a few nanometer volume. And then you can control also by appropriate engineering a number of polarization states, and you can then really actually build even what you could imagine a nano-optical vector network analyzer, where you probe in-plane and out-of-plane electric field distribution around photonic nanostructures for optical antenna studies, and really do sort of the optical analog of a vector network analyzer because we can reconstruct phase and amplitude of the light field. So this may be something very familiar to you, is what is actually the imaging. Imaging is the reconstruction of an object, and there is a transfer function which connects the emitted field distribution to the field distribution you have maybe at the image plane. The way this is in far field is that you have only propagating plane waves, and part of the issue is that you have this optical transfer function which acts as a low-pass filter. This is again the question about what type of momentum states of light we can transfer into free space. And in K-space, this is confined by the circle given by the relationship of the momentum to then your Kx and Ky momentum. This limits then how large a momentum state of the light you can collect by a given numerical aperture, and this gives you this term for the spatial resolution limit. If you, though, however, consider also all the evanescent waves, so essentially if you're trying to do the image reconstruction close enough to the object where your evanescent modes have not completely decayed yet, then you can, in some way, with arbitrary precision, reconstruct all the evanescent field distribution around the object, and then you can essentially get arbitrary spatial resolution as long as your probe or the detector is within the distance of the object of a characteristic dimension L and is actually correspondingly small. And this is why then your far field equation turns sort of then in this near field analog, where then it's wavelengths independent, and this is why we get the same spatial resolution whether we image in the UV or in the terahertz over many orders of magnitude different wavelengths, because now we are completely determined only by that dimension of this tip apex. There is a quantum optic analog to what I just described, and this is actually sort of an extension to this, which was developed by one of my students, who is actually an electrical engineer, who really had the idea that what are we actually trying to do if we're trying to locally excite an optical transition here, say, think about a two-level atom, and we try to do this in this localized form, then clearly there is also a question of how often can I cycle this atom through an excitation emission process. And this is also what ultimately limits your sensitivity. And it actually turns out, we found this experimentally, that the sharper we make the tip, the higher sensitivity we get. And at first, people thought this has to do because then your local field enhancement is larger. But it actually turns out it is because you have increasing density of states the sharper you make the apex, which you can again picture in terms of that we get larger and larger momenta, which then couple with a larger and larger momentum space of this point dipole. Right? And so this is why we then phrase this really that in the analogous language you can use is actually when you think about then antenna physics is really that we are doing some impedance matching here through this coupling from a point dipole to a point dipole to this large momentum space, and therefore really what we're doing here is really controlling the antenna load interaction at optical frequencies. Right? So this is the analog what you try to do in antenna theory, where you try to wire up, of course, the antenna to the receiver through balloons, and you have capacitors and inductors to match the impedance. So here the impedance is matched through essentially, if you imagine two point dipoles at very close proximity, then you get a very large momentum transfer of the field. Why are we actually then still efficient in terms of also the far field transduction? This is because the tip, what's relevant is not just how sharp the apex is. What's relevant is that we are driving an antenna current in an object of dimensions comparable to the wavelength. So this is analogous to what you think about a dipole antenna, that we drive this antenna current. This is what determines both the capture cross-section and the emission cross-section. Yet we are transducing to our quantum object essentially through this confinement of these optical fields. So this is really the microscopic picture of the function of the system, and this is why we get actually increase in sensitivity with increase in spatial resolution. This is a highly non-trivial concept and one of the key issues in microscopy or imaging science in general, because the higher you make your spatial resolution normally, you're probing less and less material. And so you're losing sensitivity, actually, as you increase spatial resolution. But here we are actually gaining sensitivity as we go to higher and higher spatial resolution. So this was actually really a concept which had to grow on us really over a course of a couple of years there. So we are sort of a group in some way between condensed matter physics and really optical science. And so a lot of the motivation is really, again, from the structure-function relationship in the material. Why are we developing these techniques? Because we want to understand mesoscale structure and inhomogeneities as it determines the function of many systems. So a good amount of the group actually works in correlated in quantum materials. This is where associated with quantum phase transition, whether it's a superconducting state or a colossal magnetoresistive or some multiferroic phase, there's a lot of interesting physics associated with these competing phases in these transitions. And now I'll give you an example from this work. I'll show you examples in soft matter where we probe, actually the chemical nano-imaging, then hetero-structures of organic materials where we have different organic constituents, and we want to understand their molecular interaction really on almost molecular length scales. We have worked a lot, and less so now, actually, on the whole question of optical antennas and plasmonics to really understand what I sort of summarized in the introduction about the near-field light-matter interaction. And there's still actually a lot of fundamental problems associated with this, and really a new regime of optical physics which made a lot of these techniques possible. So I'll start out actually by giving you some examples actually of also showing how high a sensitivity we can push by looking at 2D materials. Many of you have heard of this, that beyond graphene there is there's a whole class of van der Waals materials which you can exfoliate to a single layer thickness, whether it's insulators like boron nitride or then semiconductors which have very interesting excitonic and spin properties like molybdenum selenide or molybdenum sulfide and the corresponding tungsten sulfide and tungsten selenides. And what's interesting in these materials is that there are edges, there are domain boundaries, there are heterogeneities which actually limit a lot of the optical properties, and we wanted to understand these. where, of course, you can use electron microscopies and then even see down to the atomic scale what the atomic arrangement is, but you do not know how do these atomic scale defects affect a lot of the optical properties. And this is actually where this is an excellent tool to look at. We have studied graphene to some extent, and I'll show you a more recent example looking at these transition metal dichalcogenides and the excitonic properties. Because what's interesting here is that we can push the technique also one step further, not just looking at the optical aspect, but we can combine it in a more hybrid imaging fashion where we actually do control then the exciton emission by using the tip in addition to its as an optical probe, also as a nano-mechanical probe. And actually by slightly pushing into the sample, we can then, through control of the local strain, shift the exciton resonance, which tells us then which of these factors, whether it's strain or defects, control the exciton frequency and the exciton emission efficiency. So the idea actually of looking at heterogeneities in these 2D materials has been around since actually the first discovery of that we have actually a direct band gap transition with interesting excitonic properties of these materials because of the actually low quantum yield of these materials. And people were always wondering whether it's due to the effect of the edges or the grain boundaries here, which limit the emission, or some people actually see enhancement of the yield at these grain boundaries. Other people saw quenching at the grain boundaries, and we wanted to understand this. And so what we'll do is actually then we use the near-field tip sample interaction, and not only to look at the exciton emission. Here you see the exciton emergence and enhancement as we are approaching the tip within the last few nanometers. This is what I mentioned to you about where we get this onset of the near-field interaction at about 10 nanometers, and then you see this bright emergence of the exciton. You see actually a little bit the bi-exciton, but simultaneously with the exciton, we can look at the Raman emission as a probe for the lattice structure, and then from changes in the peak position of the Raman emission, you can then correlate whether the exciton enhancement or quenching is associated then with changes in the lattice. And if you actually expand the lattice, then you actually shift the exciton frequency. Is an expansion, the exciton frequency would decrease because you get decreasing band gap and vice versa, right? So we can actually do correlative imaging on these two parameters. And so we can get large field of view images in the near field. You see that increase in spatial resolution when we do the local probe with the tip. When we disengage the tip, you have conventional far field limited spatial resolution. And then we can zoom into these images and look specifically at the grain boundaries. So here is a high resolution near field scan. And what you see, for example, in looking at the grain boundaries, that we see a decrease in the photoluminescent yield. And we can resolve the width of this effect along one of those grain boundaries. And we see this is actually about a 30 nanometer channel, over which we see this quenching of this photoluminescence. We see no change in the Raman response. So this is not a trivial result of a change in the band gap and differences in the photoluminescent yield as a result of the gap size. But this 30 nanometer quenching actually corresponds actually to the exciton diffusion length at room temperature. So what this tells us is really that the grain boundary defects, which are atomic scale, very localized, as one's known from transmission electron imaging, really act like non-radiative recombination centers. We can then extend this study, and I will only just really show this very briefly. You can imagine we can study similarly the grain boundaries and the edges of the crystal. On the edges of the crystal, we see a lot more heterogeneity, actually, than at the grain boundaries. This has to do with the fact that the chemical stoichiometry of these crystals in the CVD growth is not as well defined. This work actually resolves a lot of questions about misinterpretation of signal changes at the edges. People thought these are due to topological edge state, and it's actually not the case because of that there is incomplete stoichiometry because of the diffusion limited growth. And so one can also see this in the corresponding Raman data. One interesting puzzle has always been actually, let me go back here, that we have this decrease in the photoluminescence at the nucleation site. And to address this is actually where we resort to this idea that we can now use the tip also as a local force probe and locally control the strain. And so if you start to compress onto that sample region where we have this low emission, then we actually see a shift of this exciton to actually higher photon energies as we compress. So as you compress the lattice, right, then you would actually increase the exciton splitting. And so you see this here, and then we release it again. Then to some extent the material relaxes again, and we go back to the original emission. We can also do this in a non-reversible fashion. If we push hard enough and for long enough, then actually the crystallite detaches from the substrate, and then we get an irreversible release of that strain. And we can actually, from the exciton peak position, actually quantify the amount of built-in strain in these nucleation sites. And so this really allows us really to really control through this nanomechanical interaction, both reversibly and irreversible, the strain. And it really shows that these nucleation sites really have then the photoluminescence decrease, in this case, simply as a result of the variation of the band gap, and not because of ill-defined stoichiometry, as it was thought. So the approach really allows you for a very clear and very close microscopic insight into a lot of optical properties on these types of materials. So the next example I'm going to show you is actually something on the extreme side of quantum materials, where we look at metal insulator transitions in correlated electron materials. And this is in particular on vanadium dioxide. This is work which we've done over a number of years. And one of the interesting aspects is really that in correlated matter, where you have a strong interaction between the lattice and the charge and the spin degrees of freedom, this is the material where you get a lot of these interesting quantum phase behavior, where actually, as of today, we have very limited understanding of a lot of these properties, in part because what matters is that they interact over a large scale of dimensions, from sort of atomic scale interactions of this parameter space out into both polarization, magnetization, and local strain control of a lot of these magnetic and other quantum phenomena. And so this is where we are proposing actually that using the local probe spectroscopy, that we can actually then, maybe through understanding the associated domain texture with a lot of these quantum phase transition, really understand the microscopic mechanism of these materials. And we do this both by looking at the material properties as, say, we locally control temperature and cycle the materials through the interactions, or that we can actually excite and generate new quantum states of matter by doing optical excitation with sufficiently high pump intensity. And the locally enhanced field in this case helps driving really a photo-induced change of that quantum state, and then in the evolution to then corresponding lattice distortion through the correlation with the electronic degrees of freedom to get new structure or new electronic order. So this has been something which has been proposed a lot in these in the ability to really control quantum phases in correlated matter by light, and responsible for a lot of the relevant physics of the d electrons on these transition metal ions, which characterize often in a perovskite structure the types of behavior. And people have seen associated with a lot of these types of quantum phase transitions domain, typically in transmission electron microscopy or STM. Here are some of the famous historic examples where really it was thought that responsible for this domain formation at the associated with the quantum phase transition is this interplay really of this short range at orbital type picture interactions, and then with these long range, in particular strain and magnetic domain formation interactions. And so this is potentially able to come by, because then through optical spectroscopy you can access both spatially now this sort of mesoscopic dimension, and spectroscopically then the short range interactions. And so the example I'm showing you is vanadium dioxide. This what looks like a sort of a benign insulator at low temperature undergoes actually at 340 Kelvin a sharp change to first order phase transition into a metallic phase. And really, since the early discoveries of this effect about 50 years ago, there is still no clear picture whether it's actually sort of a Peierls type mechanism where you have a structural transition, because as you undergo this electronic change, there is a structural change of the lattice from a rutile to a monoclinic phase. And so it could be a simple structural effect, or it could actually be a Mott type physics where it's really electron correlation driven. And so people have done ultrafast spectroscopy on this system for a long time, because the idea was that as you selectively pump either the electronic or lattice degrees of freedom from the time scale of the evolution then of the emergence of the metallic phase, you should be able to determine this mechanism. Yet, as of today, it has been completely inconclusive about whether it is an electronic excitation driven or a structural limited transition, and largely because people have looked at extrinsically heterogeneous samples in the form of polycrystalline thin films, and actually also to avoid this problem, we started to look at single crystal structures, and then did sort of statistical analysis on doing pump probe measurements on single crystals, and then looking at different but well-defined crystals, whether there's a correlation then with the nature of the insulating phase. And then what I'll show you then where we are driving this is really towards that we are able then to do ultrafast spectroscopy, driving the system far out of equilibrium on a local scale, really on the level of where the defects control the domain behavior, as well as where then the strain also defines what type of phase the system is in initially, and then what are the final states. So what makes this so rich, actually, this, even though benign-looking oxide, is actually that we have this fairly complex phase diagram of temperature and strain, that this metallic phase in the rutile structure actually goes across sort of a triple point where there are two insulating monoclinic M1 phases, and then separated by a certain temperature gap is a triclinic phase. And the interesting question was what happens actually as you go from this monoclinic M1 phase or from this monoclinic M2 phase, which actually have slightly different crystal structures. So we mapped out this phase diagram. Associated with this phase diagram, we can look at the volume fraction of the evolution of these nanoscale domains as we change temperature, where initially we see the emergence of an M1 phase. Then there is a buildup of internal strain, which starts to stabilize an M2 phase, and then into the rutile phase. And the interesting question is now, what would actually happen if you do an ultrafast pump-induced optical transition, where we optically induce a collapse of the band gap out of this M1 or this M2 phase? So in time-resolved spectroscopy, here looking at the reflectivity change in far field of these individual single crystals, we see that at low fluence, you get sort of a hot carrier excitation and then a coherent phonon emission and carrier relaxation. This is simply what you also would see in a semiconductor. This is a very benign behavior. Distinct then as you increase the pump fluence is that you get a transition then into a metastable phase, which is then associated with a high pump excitation in the valence band, out of the valence band in the conduction band, and then this band structure collapse. And this is then this optically induced metallic phase. And so when we study now the time it takes for this transition to happen, and then we try to vary a number of parameters, whether we are in which of the intrinsic phases, we can look at the dimensions of the crystallites, we can vary the fluence, then you see actually that you get a large variation in this dynamics. And this is too much to really describe in detail, other than you see a lot of scatter, what it seems. But if you actually take the average of this, then you actually get very good agreement with what people measured in polycrystalline thin films. I should say, though, that based on measurements of these polycrystalline thin films, there was dozens of papers which have tried to explain the single number of these about 80 femtoseconds. Some people saw it as an indicator that it's an electronic-driven process, which indicates a Mott transition. Others saw it that it's phonon bottleneck limited, because a phonon optical cycle takes about this time scale, right? And nobody saw what enormous heterogeneity actually underlies that it seems that some crystal can transition way faster than what a phonon bottleneck would suggest, but others are extremely slow. And so this was actually then what triggered us to say, well, we need to do local probe spectroscopy to look really what happens at these domains which emerge as we are undergoing this insulator-to-metal transition, which we can nicely resolve with the scanning probe imaging as we then change the temperature. And so the idea was then that what actually happens is that we have potentially defect states which are populating the band gap, and then we are either pumping into or out of these defect states, which then potentially inhibit or actually accelerate that transition into this metallic phase, which could be responsible for this large heterogeneity in the dynamics which we observed earlier. And so this is why we then do near-field pump probe measurements. So we really combine the scanning probe system now in the way we do the near-field imaging now with the ability to have an intense pump pulse, and then we have a probe where we then probe through the response the emergence of these metallic phases. And so what we'll find here is that we see that even on length scales as short as just a few hundred nanometer, we see huge variation in dynamics. You see fast emergence of the metallic phase at certain locations and the fast relaxation. Others are giving us a delayed emergence of this metallic phase. And so if you then look at the dynamics, then you see that we see within very short distances both just fast carrier relaxation and the emergence of the metallic phase, as well as sort of a supersaturation behavior. And so the other interesting effect is, in fact, that these domains, as they emerge in this case, is actually in a different crystallographic orientation as it is in the thermal-induced transition. And so what this actually really tells us that this distinct behavior of this domain formation in thermal versus ultrafast is really that there are fundamentally different mechanisms occurring which both give rise actually to a spatial heterogeneity, where we are thinking that in the thermal case it's really more a strain control, whereas for the ultrafast transitions on the order of really then the range of a few tenths of femtosecond out to picosecond is because we have oscillatory zoning with very small variations in defect concentration in these crystals, which is then actually, in this case, depending on how you define the crystal axis, then parallel to the c-axis. And so the work in some way doesn't resolve what the exact mechanism in either the thermal or the ultrafast transition is. But what it does show is that because of this large underlying heterogeneity, the origin of which we do not have a clear handle on, shows that all these theoretical interpretation over the last 50 years had to naturally be inconclusive because people simply couldn't look close enough at the microscopic details and only had sort of an ensemble average perspective of these materials. And what we are wondering really whether this is something which is specific for this material or whether it's actually general for many correlated electron materials. And so this is sort of a question I'll leave open for future work and in some way for you to puzzle about. So what I'll do in the next part, I'll really transition now to molecular materials, and then I'll conclude by showing you really one of the fastest movies, which in some way this was already a segment of it, but I'll show you one where we probe the coherent electron dynamics with extremely high time spatial resolution at the end. But first, maybe a little more for people on the molecular physics side to cover a little broader basis here is that we can actually use infrared vibrational spectroscopy or Raman to probe molecular matter in dense interactions. And so the way we do this is that we probe the vibrational transitions, which are characteristic for a particular chemical bond. But we don't just do it for the chemical identity as you do in vibrational spectroscopy, but we also look at shifts of this vibrational transition as a result of intermolecular interaction. This is a result of the Stark effect. And so this intermolecular interaction gives rise to vibrational solvodochromism. And so this is a measure for us for the molecular coupling on molecular length scales. And then again, we'll look at dynamic processes. So where is this relevant? This is relevant in a lot of biological systems, membranes where you have electron and ion transfer controlled by say, transmembrane protein, or all the way to organic photovoltaic systems where you have exciton generation, charge separation, and diffusion. A lot of these processes involve nanoscale interfaces, which we like to probe the heterogeneity because this is actually where you either inhibit or you actually accelerate or control actually this electron and charge transfer. And so what I show you really is that this intermolecular coupling, in fact, is actually what determines the nanoscale morphology in molecular heterogeneous systems. But it is then again this intermolecular coupling controlled by the nanoscale morphology, which determines then how efficient, say, charge separation or other processes occur at these phase-separated multi-component molecular systems. And so I'll focus on this example. We'll do related work actually on even on the intramolecular scale, looking at intramolecular relaxation of vibrational motion. But I think this is a good representation, and I noticed that many of you work in soft matter-related systems. So the way we do the spectroscopy here is actually sort of a heterodyne amplification of this near-field signal, we generate broadband, broadly tunable short infrared pulses, which are shining under the tip, and then we'll have a split-off component of that field, which then heterodyne amplifies this near-field signal. The result is actually that it's something analogous to infrared ellipsometry. We measure phase and amplitude of the local spectroscopic results of the material under the tip. The frequency shift, which I mentioned, is a result of that Stark effect. So the Stark detuning rate determines that then, which is a calibrated quantity, and then you can actually measure how large is the dipole field associated, say, with a chemical bond, where in the following sample we're probing this carbonyl oscillator. And these frequency shifts you expect on the order of a few wave numbers, so a few millielectron volts, actually correspond to relatively large solvent fields. So the fields between molecules are actually huge. If you've never really thought about it, it's megavolts per centimeter, which really affect that nuclear intermolecular potential. And so then from that spectral shift, you can calibrate it back and get this solvent field, in this case, actually in a condensed phase system. So the way the experiments are typically done, we first probe on a particular vibrational oscillator as a metric for the type of chemical constituents we're looking at. So then you can reconstruct a map of the distribution here of this blow copolymer, where are the domains with the polymethyl methacrylate and where are the domains of the polystyrene. And then you can zoom in and really try to understand what happens at these local nano interfaces, where you have this very dense and strongly coupled and strongly dipole interacting carbonyl functional group as it dilutes out into this polystyrene region, which has, of course, a very low carbonyl density. And so this is an example, and we had beautiful discussions actually over lunch today, where in fact we are doing this in a very brute force fashion, but there is a lot of ideas how you can actually use prior knowledge and sparse sensing and other ideas to really get the same amount of physical image content, yet by not brute forcing it the way we're doing this in this initial experiment, where we scan the sample in XY for every frequency, or you can also say we'll take point spectra at every image pixel. We then actually apply some computational approaches where we then really do an algorithm where we fit Lorentzian line shapes to the phase and amplitude at every image pixel, and then we translate this data set into a map of peak frequency and line width. And then if you do this, and you see this here, the black regions are where the polystyrene is, where there's a too low carbonyl density. But then we can then go across the PMMA region, and you see that there is actually a predominant blue shift at the domain interfaces, a clear red shift as you go into the center, and then we're going back out. Here's over 60 nanometer distance, that correlation of peak frequency and the corresponding shift, and then associated we see actually almost factor of 2 doubling of the line widths. This means that the vibrational lifetime is greatly reduced as we increase the coupling between the carbonyl oscillators in the center of the domains, and then we can go back. And so we can then really quantitatively analyze this picture and determine then at these domain interfaces, where over a few tenths of nanometer distance we get this rapid change in line width really over molecular scales as this coupling greatly decreases, which leads then to this line width narrowing or to that corresponding shift in frequency, which we use as a metric of the change in this intermolecular field strength. And if you see this, that over a distance of 10 nanometer, the intermolecular field really changes from about 4 megavolt per centimeter to 2 megavolt per centimeter. So really, between molecules, there are gigantic local fields, and this is why it's no surprise how extremely sensitive a lot of biological processes are to activation potentials, to certain salt concentration, and also in organic photovoltaic systems, how extremely sensitive one is to molecular orientation at these interfaces, which control exactly these field processes. And this is really the first time we were able to really get a microscopic view of the distances and magnitudes of these local fields over these very short length scales. So let me actually skip this part and then tell you a little more how we can get more microscopic information, not just about the chemical composition and this coupling, but also molecular orientation. We can do this by then measuring relative to the tip orientation whether vibrational modes are actually enhanced or decreased. And this depends on the orientation of this transition dipole moment with respect to the tip axis. The tip predominantly is sensitive to a field parallel to the tip. And so depending on a molecular bond transition dipole moment being parallel or perpendicular to the tip, from the corresponding signal you can then determine the orientation of this molecule. This is analogous to what we can do also both in soft matter. We can do it with the Raman tensor in solids. We've actually done this in ferroelectrics and being able to map spatially ferroelectric domain order by the phonon selection rules in nanocrystals, depending then on the crystallographic axis. Certain phonon Raman modes or phonon modes are Raman allowed, others are forbidden. We can do this in proteins, whether we look at transmembrane proteins, which have a preferred orientation normal to the membrane, and we can image this. Again, we can do spectroscopy on these on the amide mode, looking at this membrane transmembrane protein distribution, and from that we can actually learn from the spectral response, where we only see what's called the amide 1 mode, that indeed these with these two modes in the protein being orthogonal, that in these membrane layers the molecules are actually oriented in this fashion. We can then look at disorder and distribution of those, and then get corresponding spatial distributions and defects in these membranes. We can do this then also in molecular electronic systems, where we can see in these types of two-dimensional molecules where it's very sensitive, depending on the stacking, in which direction you get electron transport. And so there's a lot of problems associated with the disorder in these molecular electronic systems, built in this case out of these PDCDA molecules. And so here's a good example where, by looking at the transition dipole moment, again probing the carbonyl, which is in plane, and then there is an out-of-plane motion of the carbon atoms of the CH mode on these on the phenyl side. And so by looking at the ratio of the CH versus the carbonyl, we can reconstruct the orientation and really the Euler angle of these molecules under the tip. And this allows us then, in heterogeneous films or single crystal structures, really determine the molecular orientation and really do optical infrared crystallography on the nanoscale on these with this type of spectroscopy, looking at multi-vibrational modes simultaneously. And so here, by combining the spectroscopic data, including different scanning probe signals on these different references, and mapping and binning these in appropriate distributions, we can really get a spatial distribution map of the molecules here, a disordered electrode interface, where we see 3D islands where the molecules are flat, and then at the edges we see a lot of disorder, where then we get molecular aggregates of different order. And this is why then, if you have charge transport, which is predominantly in plane, that suddenly we get inhibition of the carrier transport as we go into the electrode interface. So in the last minute or so, is that good? Yeah, okay. So I'll show you then what I sort of want to loop back to what I showed in the beginning, that really one of the elementary processes of the electron dynamics is really in metals, where you have this extremely fast scattering time and these extremely short time scales. And so then this was really a challenge for us to say, can we actually really see this? Can we visualize the effect of carrier scattering and the associated dephasing of a coherent excitation on this time scale with that corresponding length scale, and then really see elementary interactions of the optical excitation in a metal. And so for this, actually, this was also many years in the making. We really conceived this tool where we really wanted to have a femtosecond pulse really confined at the apex for spectroscopy, appropriately spatially confined, and then really with control on the single cycle limit. And it turns out that this tool exists really in the form of the idea of adiabatic focusing, where we can actually launch a propagating surface wave on the tip shaft, which then compresses into this apex field. And I won't talk much about the details of this tool, but just really show you that we can really use that femtosecond localized light source in four-wave mixing, actually, to image, in this case, at a gold metal edge, the coupled plasmon dynamics in real space and time. So if you drive a coherent plasmon excitation in the form of a collective charge density oscillation in sort of localized regions of the sample. So we can excite one here, we can excite one here. There's a small one actually behind. So you see from the corresponding signal the localization of this emission. So these are localized surface plasmons, which are coupled both through space behind the continuous film, but also then through space through some amount of dipole-dipole interaction. They may have different frequencies. And then also we have radiative emission of these emitters. And so we want to watch really the emission of these, or the coupled dynamics of these three surface plasmon in space and time. And so what we'll do there, we have multiple pulse sequence, which then leads to the coherent generation of this four-wave mixing signal. And as we pulse delay one respect to the other, we can essentially turn a movie. And so what we do here is we normalize the signal to the center emission of this, and then you'll see that really as we are stepping through, this is with single cycle precision. I want to remind you that in time-resolved spectroscopy, even though these are 10 femtosecond pulses, the time resolution is not a question really of pulse duration. It's a question of signal to noise and the precision with which we characterize these pulses in phase and amplitude. And then you can really see that we see this decoherence of these coupled plasmons. You see a little emergence here back of a propagating mode responsible actually for the fact that these two are decaying slightly faster and transferring actually some spectral weight to the center one, which slows down this emission. So this is really the fastest movie. It's a short sequence, admittedly, over a very small length scale, but with the highest time resolution and the fastest temporal resolution. So we can extend this tool in many ways to different capacities. We use actually the second harmonic response of the apex for a pulse shaper, which then by which we actually generate these pulse replica. This mode compression associated is a fundamental interest itself. It's actually a result of a divergence of the effective index of refraction, which gives rise then to a decrease in the group velocity. So the group velocity by the time the field reaches the apex is only 20% of the speed of light over a broad bandwidth. Ultrafast slow light is actually hard to make because often you rely on electromagnetic induced transparency when you want to make slow light over narrow spectral bandwidth. And we can actually use this strongly confined field at the apex and also actually as an electron source. The strong nonlinear interaction, which we're using for four-wave mixing, is also giving rise to the nonlinear emission of electrons. So we can actually generate short electron pulses. This is actually work in collaboration with groups in Berlin, which we then use for point projection imaging. And we just actually got 40 femtosecond time resolution in pump probe with electron imaging. So this is actually why also a lot of the techniques I mentioned in the beginning, whether you do X-ray, electron, or optical nanoprobe, they do connect and really allow you also for new imaging modalities by combining these different capacities. So where we are pushing the technique now is really to do single molecule ultrafast spectroscopy. We are currently already at the single molecule limit. We can probe single proteins in IR spectroscopy. This means that we are sensitive to about 400 vibrational oscillators. This is an increase of about 10 to the 6 compared to actually far field IR spectroscopy. We can extend the technique to different multi-dimensional spectroscopies, where we then also use the four-wave mixing signal to the coupling behavior between different constituents, either in hard or soft matter. The realm of quantum materials is particularly attractive because there are comparably few tools which can access these coupled degrees of freedom in these materials, and this is really where in condensed matter physics increasingly groups adopt this technique because of the ability to probe both in the spatial and temporal domain and also really look in particular at ferroic order. And so this is sort of, again, the summary of what I'll talk about and what sort of our theme in the group is really this optical antenna-based technique where we take advantage of the near-field impedance and quantum load interaction, really as we coin it, and to study either a number of material properties or actually develop the technique further. And I really encourage everybody to go into this field, really. There's a huge regime, and largely unexplored, of optical physics in the near field. This connects a lot to what you know from cavity optics, how we control density of states. There are fundamental differences actually in the thermal near field we started to study, which actually also connects to a lot of fundamental properties in quantum electrodynamics, in particular the Casimir and the Casimir-Polder forces, which are near field phenomena. And then there are really interesting effects pushing to larger fields, which gives rise to strong coupling because of the high density of states, and then cavity QED effects and other phenomena. So reaching then also outside of sort of a lot of the conventional room temperature measurements, which I showed you, then to higher fields and lower temperature really would open a whole new field of physics. So with that, I'd like to thank for your attention and all showing. Right?
Thank you. Any questions?